ребята говорят, YouTube не настроен, не идет transmission.
Сейчас как раз настраивать.
Ага, ну там подождем сюда.
Sorry, like just a technical delay, a few minutes, so we just need to set up the YouTube online translation.
Какой дедлайн? Как Павлос Логудакис, plenary session 3. I will.
Just see what he's doing.
So we need to switch. Ой, нам нужно переключить этот. У него свой там экран. У него есть свой экран. Нам обязательно, чтобы нас транслировали. Ага. С кофейком. Растворимый, что ли? Или наш? Не наш, чувствуем. Ну, все нормально, да? А трансляция пошла?
Yeah, no problem. This one is working.
Okay, beautiful. Dear scientists, dear colleagues, sorry for the technical problems. Everything is fixed now. We're translated to YouTube online. I'm delighted to introduce you to our speaker, plenary speaker, Professor Pavlos Lagoudakis from Caltech University and also University of Southampton, our neighbors from Exeter, near Exeter. We actually have the closing plenary session today. This is the third day of the conference, and it's fantastic that Pavlos is actually closing this day and this plenary session. And Pavlos actually was one of the plenary speakers at the London POEM conference. As I remind you, SPb-POEM is a spin-off of the London POEM conference. Thank you very much for making it for the second time. I understand this talk is going to be a little bit different. Thank you very much for changing it, and we are all looking forward to hear it. Thank you very much for coming. The stage is yours.
Thank you very much. Thank you for the introduction, and it is a pleasure to be here at this historic place now, where I will be talking about ambient polaritonics. So, as we heard in the introduction, recently we have been working on polariton simulators and polariton lattices, but in collaboration with IBM, we have ventured into room temperature polaritonics, and the applications of those into transistors and logic gates. So the work that I will be presenting here today was performed predominantly by Anton Zasedatelev and Anton Baranikov from Skoltech, and now Anton is at the University of Southampton, in collaboration with IBM in Zurich. And before I move on, let's see, yes. Okay, just a brief introduction at the operation of this lab, so this joint lab between Southampton and Skoltech. We have at Skoltech, this is a preliminary building where we have moved in the last couple of years, and where we are really working towards applications. It is a technologically based university, and at the University of Southampton we really study mostly the fundamental properties of polaritons and strongly light matter coupled systems. So this is July 2016, when we were allowed to go into the room where we built a lab, a photonics lab, where actually the work that I will be presenting today was performed in there. So this is really the setting up of the optical laboratory. It took actually a couple of weeks to set up just the optical bench, and then very soon later on we had arranged for delivery and installation of the lasers, and here we are just after the installation of the table in September. And Anton here, he was really the driving force together with Anton Baranikov of the work that I will be presenting here. So if I go to January 2017, a few months later, the lab is already up and running. So we had really organized the delivery of equipment, etc. And the work that I will be presenting here concerns ambient polaritonics, so polaritons at room temperature and ambient conditions. And this is really the setup on which the experiments were performed. So a short ad about the work that we are doing in order to instigate also collaborations with you guys here. So we are working on hybrid organic and inorganic photovoltaics and LEDs, and this is really the most applied part of the work, but really the thrust of the work is on polaritonics, where we work with room temperature polaritonics, polariton simulators, quantum polaritonics, neuromorphic polariton computing, polariton logic with IBM Zurich. And we embed polariton condensates in lattices. We study the interaction of the lattices and phase transitions between different types of coupling, and we have also developed algorithms to modulate polariton condensates in real time so as to program our simulators and computing devices. Now, with no further ado, for those who are not familiar with the field, I will give you a brief introduction to what are polaritons. So polaritons are quasi-particles which occur in semiconductor microcavities. So if I split my structure down, it consists of a Fabry-Perot into which I confine the optical field. This Fabry-Perot is not with two metallic mirrors, but with two distributed Bragg reflectors of very high reflectivity. So if I look here at the reflectivity as a function of wavelength, you see that I have a very broad stop band with almost 100% reflectivity and a cavity mode occurring more or less in the center of the stop band. Now, the cavity, as we would know from Fabry-Perot physics, it allows me to access at normal incidence the cavity mode, but I can excite or detect light at an angle to the cavity, and that allows me to see what happens to the in-plane projection of the optical field. Now, what we do in these structures, we embed quantum wells, or a semiconductor which has an optical transition resonant with the cavity. So when we do that, we confine the electronic transitions and the optical field in a very small volume, and when the interaction omega between the photon and the exciton, the electron hole, the electronic transition, is becoming stronger than any dissipation mechanism inside the system. Here, just for describing the system, I have introduced two of these dissipation mechanisms: photon decay due to the finite cavity lifetime and exciton decay inside the system. Then, once this coupling exceeds these losses, we enter the strong coupling regime, where if you look at the reflectivity, instead of now looking at the exciton or the photon mode, you look at the Rabi mode splitting of two coupled modes. So these are the new eigenstates of the system, the upper and lower polariton mode. So we have normal mode splitting here. And of course, for those who may not be familiar and have already lost me, I have here borrowed a video that we made. So I have an exciton and electron hole pair in the semiconductor. Now my photon will create an exciton. The photon will go back and re-excite an exciton. The exciton will emit, and back and forth, back and forth. When this interaction is faster than any other process inside the system, then we will enter we will enter the strong coupling regime, where we will not be talking anymore about photons or excitons, but about this new quasi-particle, which is the polariton state. Okay, so a bit more rigorously, if I were to describe the polariton, it would be the admixture of a photon with a given weighting factor and an exciton. Now, these weighting factors are the Hopfield coefficients, and from those I get that from the photon part, my polariton has a very low effective mass. So it is a very light particle, and it also has a very short lifetime, which is defined by the cavity lifetime. So even if we make very high Q cavities, we cannot really bring it beyond 10 to 100 picoseconds lifetime. Now, from the exciton component, it takes very strong interactions, and through these excitonic interactions, we have polariton-polariton scattering, and that is an important mechanism for relaxation of polaritons. Now, if I take the two states that I have in the system, the two eigenstates that I have in the system, the exciton and the cavity, and I couple them, then by diagonalizing this Hamiltonian, I get the new energy modes in the system. And I see immediately that I have two energy modes. One is called the upper polariton, and the other is called the lower polariton mode. So the exciton and the photon, when they are in resonance, they give you the splitting, and that is described here at normal incidence to the cavity. So what happens if I look at an angle? Well, if I look at an angle, I would have to look at the dispersion of the system. So here I have plotted with a green dashed line the bare cavity dispersion. Now, you will be familiar with a conical dispersion for the photon field, but once you confine to one direction, then practically you get a parabolic dispersion for the optical photon, the cavity photon. Now, the exciton is also a parabola, as you would expect from the kinetic term, but because it is much heavier than the photon, for the range of angles that I can access, and I plot it here from minus 60 to 60, it is completely flat. So if I bring at k equal to 0, or at normal incidence, at 0 angle, the exciton and the photon in resonance, I get this normal mode splitting that I described here, and as I move the angle of detection, I see that the splitting is changing, of course, because the resonance is changing, and I now form not just two distinct energy states, but two dispersions. So I have the lower polariton dispersion and the upper polariton dispersion. So this is a system now that allows me to play with the dispersion, the energy momentum relation inside the system, just by changing the detuning between the photon and the exciton. Okay, so this is really a basic introduction on what are polaritons. Polaritons, as I have described them so far, they consist of a photon, which has a spin of plus minus 1, and an exciton, an electron hole pair, which again has a spin of plus minus 1 if it is to be excited by a photon. So it is a bosonic quasi-particle, and as a boson, it could potentially form a Bose-Einstein condensate. And that was predicted in 1998, and in 2006, the group of Benoit, Devoux, and Lesidang, at experiments performed at the PFL, they observed the first condensation of polaritons at cryogenic temperatures in an inorganic structure. So here you can see the dispersion energy as a function of in-plane momentum. This is the parabola that we were looking before, but focused in a small angle range. And as they increase the excitation density and they pump non-resonantly an incoherent polariton exciton reservoir, the relaxation gives emission from polaritons, and at some point, as they increase the excitation density, they hit threshold for condensation. Now you get stimulated relaxation of polaritons at the ground polariton state, and that forms a Bose-Einstein condensate. And in this Nature paper, they described all the properties of these Bose-Einstein condensates, which is a Bose-Einstein condensate in a dissipative system, but otherwise it really has many similarities with what you may know from atomic condensates. Okay, so this was really at the cryogenic temperatures using cadmium tellurium microcavities at Southampton in 2007, a year later, and in collaboration with a group at EPFL that makes gallium nitride microcavities, we obtained the first evidence of polariton lasing at room temperature. Now, we used gallium nitride because I have much stronger exciton binding energy, and therefore my exciton can survive all the way to room temperature. It is not actually dissociated by the thermal by the thermal excitations. And in 2014, there were two papers that came back to back, one from IBM and the other was from Stefan Meyer's group in collaboration with Ken Cohen from Imperial, where they had replaced the inorganic material, the gallium nitride that we placed in the cavity, with two different types of organic materials. And they observed all the signatures of Bose-Einstein condensate of polaritons at room temperature, but now instead of using a crystalline semiconductor, they were using amorphous organic materials. So practically this is the first evidence that organic semiconductors can really operate and bring you the physics of Bose-Einstein condensation at room temperature. So, to summarize polaritons, they are the result of strong coupling between cavity photon and an exciton. They offer you direct access to the properties through photoluminescence. So the photoluminescence that you see here really carries all the physical properties. So it carries the energy, which you see here on the dispersion, the momentum, which you see on the in-plane axis. It carries the spin if you do polarization resolved measurements, and if you do interferometry, it also carries the phase. There's nothing else actually that you would like to measure. And you can do all that in situ, without having actually to tamper with the condensed state. Polaritons leak with the cavity lifetime in the form of photons, and they carry all the properties. And the photons are what we are detecting. Okay, so what are the applications now of polaritons? Well, if you have a polariton condensate, you understand, you increase the pumping density, and at some point you form a coherent state, and strong emission comes from the polariton mode. So what we wanted to look into is if we can use polaritons as amplifiers or transistors. And there has been a very nice review by Miller on the all-optical transistors and their applications, really what characterizes an all-optical transistor. And already back in 2000, in a pump probe configuration in an inorganic structure at Southampton, Pavlos Savidis realized the first polariton amplifier. So they were pumping resonantly at the inflection point of the dispersion, and they were probing at the ground polariton state, and that was stimulating per polariton scattering and emission from the ground polariton state. So this amplification was a factor of 100. It was early days for the field of polaritonics, but later on in 2013, the group of Danieles and Vito, again in an inorganic microcavity at cryogenic temperatures, they were playing with the in-plane propagation of polaritons in the plane of the structure, and they configured an optical polariton transistor, where they showed at cryogenic temperatures some amplification and logic gate operation. Now, in 2017, there was actually a very nice review at Physics Today by David Snoke and Jonathan Keeling, where they were talking about the hallmarks of polariton condensation in organics, which are there, but parametric scattering, optical amplification had remained elusive. And actually, we had been trying for many, many years to achieve this kind of amplification or a transistor operation with organic structures, but to no avail. So, why we couldn't get it for so long? Well, for that, I will just take you through the materials medley that we have, so the different materials that have been used for organic microcavities. And the different materials consist of, can you actually see well the screen, or do we need to turn the lights? Yeah, if you can dim the lights, because the next we will have actually some slightly lighter images. So the first materials into which polaritons were observed were inorganic structures with gallium arsenide, cadmium tellurium. Here we have Vanier-Mott type excitons, so we have delocalized excitons, and we have per polariton scattering in the relaxation process. Now, later on, we observed polaritons in gallium nitride, zinc oxide semiconductors, where we have very strong exciton binding energies, and therefore polaritons can survive at room temperature. And finally, as I said earlier, we can put organic semiconductors inside microcavities. Now we have even stronger exciton binding energies, and we have very strong molecular vibrons inside the system, and again, we get polariton condensation. So this is the system that I will be talking about. It offers room temperature operation with very large binding energy, very wide material set. You are not limited to one material, like gallium, for example, here, nitride or zinc oxide. There is already a very broad range of organic semiconductors that have given rise to polariton condensation and strong coupling, and the high oscillator strength. The interaction of the optical field with the exciton in organics is very, very large. Okay, so starting really from the seminal work of David Lidge in 1999, where he observed for the first time strong coupling in a J-aggregate microcavity, the field has boomed, and different materials, proteins, dye molecules, oligopolymers, polyfluorines have really been used now to observe strong coupling. And here you can see actually the benefit of having such a big library of materials that you can use in organic semiconductors. We can get polariton lasing from 2.1 to 3 eV just by using a different material system. So it is a very flexible platform. Now, in order to get this polariton laser or polariton condensate, and I will be interchanging between the two terms, you need to excite non-resonantly and somehow create a condensate at the ground polariton state. So you can start with interparticle scattering, so this per-polariton scattering that I was talking about from the work of 2000. However, this actually, in the case of organic semiconductors, it does not work because you have localized excitons. The excitons in the organic semiconductors, they are pinned on the molecule, and therefore fermionic exchange interaction is quenched. So weak per-polariton scattering in the organics. You can have intracavity optical pumping. So as I said, we have very high oscillator strength. If you can tune the fluorescence to be resonant with the polariton mode, you have uncoupled molecules in the system which pump resonantly the dispersion, and then if you tune the dispersion resonant with the gain of your system, you could get polariton lasing. So this configuration favors negative detuning, and the first observation of such polariton laser was done in 2010 by Kenna Cohen and Steve Forrest from Michigan, now at Michigan. And then there is vibron-mediated relaxation. So you can induce an exciton reservoir, and then you can use strong vibrational modes on the molecules, on the organic molecules, to dissipate energy and relax on the polariton dispersion. Now, molecules, they are characterized by a discrete spectrum of these vibrons, and they carry a lot of energy. So you can really dissipate hundreds of milli-electron volt just with one scattering event. Now, back in 2011, we really studied this process in some detail, and we found actually that with time-resolved studies, I will not go into detail here, we found that it accelerates the relaxation on the polariton dispersion, and we could correlate the vibron resonances with the Raman spectrum here in black with the photoluminescence intensity or the rise time of the photoluminescence at different positions on the dispersion. So we understood back then that vibrons accelerate the relaxation of polaritons, and that is actually what we would like to use, and what I will be using now in order to create polariton condensates in this MELPPP structure. This is a material grown at Wuppertal by Uli Seff, and the first microcavity was this made in 2014 that showed polariton condensation. So this is our structure. It has very strong vibron modes. It is a ladder-type polymer, so it is not a flexible molecule. So any vibrational mode there, it is very stiff. It carries a lot of energy, and you can see here two distinctive vibrons. Vibron 1, it carries 164 MeV. Vibron 2, almost 200 MeV, and these are the ones that we would like to see if we can utilize. So here you can see now in the strong coupling regime, so you can see the polariton dispersion, because you have two modes here, you couple with both of them, and you see that you have three polariton dispersions, lower, middle, and upper polariton mode. You get a very large Rabi splitting, and we will be operating in relatively negative detuning. So with this structure, back in 2014, similar in the way that was done in 2006 with inorganic structures, the IBM group observed polariton condensation under non-resonant excitation. So all the signatures of the intensity, nonlinear intensity increase, a blue shift and light width narrowing, everything was actually, everything was reported in this study. It was a very, very nice work. And they also showed that the distribution of excited states follows a Bose-Einstein distribution. So now what we will be doing, we will be trying to use this vibron to accelerate the relaxation to the ground polariton state. So we will be pumping quasi-resonantly, and we will be tuning the pump to be one vibron above the lower polariton mode. So in this way, just with one scattering event, I can take a hot exciton straight into the condensate, and therefore we will be pumping at 2.8. And what you see here is the dispersion when we pump here below threshold, so I get a nice distribution of polariton photoluminescence on the polariton dispersion, and when I go above threshold, I get a collapse and a blue shift at ground polariton state. So if I characterize this, I have all the signatures of polariton condensation, so the nonlinear emission, the line width collapse with the red here, the energy shift with the blue, and so all the features that in the polariton community we consider as hallmarks for condensation are here. And we also observe that the threshold when we hit resonantly with this vibron mode is 1 order of magnitude than when we do it completely non-resonantly. So in the IBM work, they were pumping at 3 eV. They had a lot of scattering events in order to create a condensate. Now, by utilizing this vibron, we have an order of magnitude lower threshold. So what is the role of the vibron? Can we study it? For this, we have done 2 experiments. In the first experiment, we are fixing the pump on the transition, on the molecular transition, resonant to the exciton, let's say. And now we change the detuning. And as we vary the detuning, we record the emission from the lower polariton mode. On the top, you see the Raman spectrum. And you see that every time that I hit a vibron, I have enhanced photoluminescence coming out of the system. So indeed, the vibron plays a role in the relaxation. I can do the reverse experiment. I can fix the detuning and now vary the pumping energy. And this is pictorially shown here. So here are the 3 dispersions of the system. And I will be changing the pumping across the vibron resonance. And you can see that when I hit the vibron, on the horizontal axis here, it is in a logarithmic scale, I increase dramatically the polariton occupancy. So having understood that the vibrons play a very important role in this polariton condensation, when you excite quasi-resonantly, we will be doing now a pump probe experiment. So we'll be pumping the hot exciton, and we will be seeding with a control beam the ground polariton state. So we want to really seed few polaritons in order to kickstart the stimulation to the polariton condensate. And for that, we have devised a non-degenerate pump probe setup, which we can discuss later if you are interested. So with this, what we can do, we can send a probe which is resonant to the ground polariton state. We can have a pump which is non-resonant. And when the pump is below threshold for pump-only condensation, in the presence of the probe, we see here already that we can get a polariton condensate. So this seeding process works. So it is like we send a control beam and we amplify this control beam. And we get again all the hallmarks of polariton condensation, so the nonlinear photoluminescence, the line width narrowing, the energy shift. And this is now in this pump probe configuration. So what I show you here is what happens when I have the pump only. So when I have pump only condensation, and I compare this with pump and seed, and the efficiency of the relaxation when I seed the ground state becomes dramatically stronger. So you can see this here with the blue curve is the pump only photoluminescence from the ground polariton state. The red one is pump and the control beam, and clearly the threshold is shifted. So we have twice lower threshold, 50 times rise in the relaxation. If I compare here the emission intensities that I get, plus I can get polariton condensation on demand. This means that I can be pumping non-resonantly the exciton reservoir below threshold, and only when my control beam is there, I can seed a polariton condensate. So this is what I will be using now as a polariton amplifier operating at room temperature. So I have the pump, I have the signal, and the signal is being amplified. And you can see here the amplification. The probe alone is multiplied here by 200 in order to be visible, and we have huge amplification of the signal. You can see here the signal amplification or net gain as a function of the fluence. So we get a record gain of 10 dB per micron. This is the highest gain ever reported in any optical amplifier. The system does not require phase matching, so we do not really need to tune the angle of the pump to hit a particular polariton resonance, because we pump the hot exciton reservoir, which is dispersionless inside the system, and we operate at ambient conditions. So we have all the hallmarks of an amplifier, a polariton amplifier, at room temperature that does not require phase matching conditions. And now, I do not know if you can see this, if we compare optical amplification in terms of net gain, you see that this system actually carries by far the highest gain than any other system, including fibers, VCSELs, quantum dot amplifiers, etc., etc. Okay, so if you want now to talk about a transistor, what you would like to have is to be able to cascade your signal. So you take the condensate out of the sample, and you want to be able to bring it back into another amplifier and do cascaded amplification. Now, to do this, we devised a double pump probe setup, which allows you now to take the condensate emission out, and you can bring it back in, and that waits you another non-resonant pump to amplify even further. And this is the result here. So you take the emission out. So this is the address state. You bring it to another position on the sample. In the absence of the pump, you see that there is practically no light. In the presence of the second pump, you see that you have actually cascaded amplification of the original signal. So we have cascaded amplification. The next thing that I would need to show in order to talk about a transistor would be ultra-fast switching, or switching in general. So now I have my pump, and I get the state that comes out. In the presence of the probe, I have very fast and very short pulse coming out. So this is here, you can see the 0 and 1 state within, in less than a picosecond, so around 400 to 500 femtoseconds, I have the switching on and the decay of this amplification. So it can operate as an ultra-fast switch. So if I put everything together, I have really put together a polariton transistor now, because I have shown you optical amplification, cascadability, ultra-fast switching, and of course what I would like to have is a good extinction ratio, because we are talking about optics and there is scattering when we talk about optics. So here what I show you is the extinction ratio as a function of excitation density, which approach is actually 17 dB. And this is a good enough extinction ratio, very easily to be able to distinguish between scattered light and really the amplification. Now, having a transistor, you need to take it to the next step. That is interesting, but really our system would not work as an amplifier. It is an organic structure. It would not replace your OPA if you're thinking about that. So we are venturing into logic gate operation. So now we are putting together a triple pump probe, not a double pump probe configuration, where we have a single pump amplifying either one of the two input states of an OR gate, and the outputs come and they mix together at a different transistor, and then I have another pump which will amplify the signal. So in this configuration, I have 0, 0, 0, etc., etc. You understand the OR gate. So here what I'm showing you with the red curve, if you focus on the red curve, it is the emission as a function of control power when the pump only is above threshold. And there I see that I have more or less an analog amplification. And this is important here because it will allow me to operate in the OR gate configuration and really get an output on state 3 when either of the two or both of them are present. Either of the input channels are present. Now we will go to the AND gate configuration. That is actually more tricky to operate because you want to have amplification only when both inputs are present. And now we will be working with the pump below threshold where I get a digital, if you like, amplification. And again, we have shown that the system can operate as an AND gate. Now, if you have an AND and an OR gate and someone asks you to do an operation, it becomes actually horrendously difficult. You need a very large number of those in order to do any even simple arithmetic process. So what we have been looking into is if we can really configure a universal gate. A universal gate is a NOR or a NAND gate, and that's the gates that your computers in your hands and your phones operate with. So in order to configure now a universal gate, what we are looking into is having a system that will be switching off when I have either of the outputs of the inputs there, and it is there in the absence of any input in the gate. And for that, for the first time, we realized non-ground state polariton condensation. So I will take you through the physics first, and then I will show you how the configuration works. So far, the probe beam, the seed, was at k equal to 0 at the ground polariton state. But what happens now if I put the probe resonant at an angle? So you see here the probe resonant at an angle, and in the presence of the pump, or as I increase the non-resonant pump, I can get this amplified. So now I have tuned practically the vibron to take me from the hot exciton to a non-zero in-plane wave vector in my system. So I see here again that I have the nonlinear emission, I have the collapse of the full width at half maximum, I have an energy shift, all the hallmarks of polariton condensation inside the system. And now what I need to see is what happens if I have my non-resonant pump above threshold. Is this enough to switch is the presence of the probe enough to switch it off? So now we have a single pump probe, but the probe is at an angle, if you like. So if I have the pump only, I get a very strong condensate from k equal to 0. In the presence now of the probe seeds the condensate at an angle, and therefore the emission from k equal to 0 is quenched. And you can see this here. It's quenched by a factor of 10 already. So here we have done the full characterization. So this is the angularly filtered emission in the presence of two probes. So now I can have a probe at plus an angle and minus an angle. Yes, plus and minus wave vector. And in the presence of two, I get, again, a very good extinction ratio. So if I plot here the extinction ratio, it becomes now something like 13 dB. So in the presence of either of the two probes, I can quench the condensate that it is injected by the pump, the non-resonant pump. And that is nothing else but the NOR gate. So in the NOR gate configuration, when both inputs are 0, the output is there. And in any other configuration, when you have either of the two inputs inside the system, which in our case is a probe beam at non-zero wave vector, the condensate is switched off. And this is really the NOR gate. Now with that, I will conclude by acknowledging the people who really contributed to the work. So Anton Zasedatelev with Anton Baranikov were the driving force in the lab, Ulisse for the material, and the group of Thilo and Raine from IBM for the structures. Our funders and you for your attention. Thank you.
Thank you very much for an exciting and brilliant talk, as always. Thank you very much. Let's start with the questions. Sorry again for the delay, for technical problems. Would be the first. I will, oh yeah, okay, okay, sorry, yes.
Can I ask about you that there are three lines, but not two? Why speed?
That's a good question. So I can describe this easily with my hands. If I have one exciton and one cavity mode, I get a normal mode splitting. If I have two exciton lines, yes, and one cavity, I get strong coupling with both excitons. And that gives you actually three polariton modes, yes? So the two different states, the S1, 0 and S01 in the case of the organics, they both couple with light and they give you this. Yes, yes.
So if we have excitonic series, so it will be the line which is presented in excitonic series, yes? The number. Okay, thank you.
Yeah, okay, thank you for the talk. You showed several maps of intensity, so I didn't mention what are the scales, how big are these maps, like when you have this 0, 1s and...
So the smallest that we can do our condensates, yes, is really, we are limited, we are resolution limited, so we can bring it down to 1 micron. So really the intensity, so if you like, each transistor would be a very large one because it would be, it's optical transistor, it would be down to 1 micron.
Yeah, but that's because of just limitation of the resolution.
Actually,
yeah.
yes. So we cannot focus our beams, and the polariton wave function, of course, which is really driven by the photon, the wavelength of the photon part in the cavity. So this is really what drives the size of the spot, which is in our case, the size of the transistor.
Yeah, but theoretically, if it would be possible to make it smaller, you would be able to make it...
Yes. So if we could really operate with microstructured devices, because now we are dealing with a planar device, and therefore you are limited by the resolution, the optical resolution. If we had microstructured devices, we could compact it even further.
Okay, thank you.
Thank you very much.
If I understand, when the system condensates, you have a shift, a blue shift compared to polaritons, and you say you excite resonantly polariton plus vibration, but and you have a shift after of condensation. Does it change the excitation, the energy of excitation necessary? Is it
very good question. So what? If I repeat the question for those who didn't hear, when we pump non-resonantly, we see that the emission from the ground polariton state is blue shifted. And the question is, does this actually disturb the pumping conditions, and do you need to compensate for the pumping conditions? The answer is no, because the vibrons are, because the excitation beam is quite broad, so we are within that. The origin of this blue shift that we observe is something that we have actually just submitted a paper where we have done an extensive study to understand what is the origin of blue shift in organic semiconductors. Because as I was telling earlier, in the case of inorganic structures, due to the fermionic exchange interaction, you have strong exciton-exciton scattering, which blue shifts. It gives you a potential landscape. It creates a potential landscape in the structure. But such fermionic exchange is not present in organics. And we understand now what is the origin. It really has to do with a quenching of the vacuum Rabi splitting and the competition with an intermolecular energy transfer. But it goes beyond the scope of this talk. We can talk about it later. Thank you.
More questions? Okay, so I thank you very much once again. I suggest we continue the networking and discussion of this excellent talk after the next session, which is actually going to be the last session, but we'll still have the coffee break after that. So I'd like to welcome the chair for the last session, Professor Michał Hadzinski. So we have quite some change of the program. So the last session, session 3, is will not happen, and the talk by Georgy Ermolaev from the Moscow Institute of Physics and Technology will be at the end of the next session. Okay, so let me thank Pavlos once again for his brilliant talk. And Professor Hadzinski, I give you the microphone. The stage is yours.
Thank you. Let's continue the session. The first talk will be given by Professor Vyacheslav Polyakov from MDT Spectrum Instruments, Russia. The title of talk is Scattering Scanning Near-Field Optical Microscopy of Nanomaterials in Visible, Mid-IR and Terahertz Spectral Range, please.
Thank you once again for the introduction. And, well, first of all, I would like to thank organizers for giving a chance to have this talk that is actually about the scanning near-field optical microscopy in different spectral ranges. And during this talk, I will try to cover two large parts. After a brief introduction, I will talk about the not exactly the optical measurements in atomic force microscopy, but the quite basic stuff about the AFM, about the taping mode AFM as a basis for the scanning near-field optical microscopy. And then I will switch to the second part of the presentation about the examples of applications of scattering SNOM in different spectral ranges, starting from the visible spectral ranges, infrared range, and even some examples of the terahertz applications. So the atomic force microscopy is not the young technique. It is already more than 30 years old, and it is widespread because of its quite wide abilities and its large potential. Typically, the key idea here is quite well known. You have the sharp cantilever that it's usually fabricated from silicon and can be, depending on the application, covered with the different materials. And by measuring the kind of interactions and apply some different external fields or temperatures or whatever to the area of interaction of the sample under investigation and the probe, one can get a lot of the properties, one can image a lot of different properties of the sample, starting from its regular topography and down to its nanomechanical, electrical, magnetical properties. What's important here is that it can be combined with a different kind of illuminations in different spectral ranges, starting from visible one and up to infrared and terahertz radiation. And actually, a lot of properties can be measured using AFM, and in marketing kind of purposes, we usually say that there are more than 50 AFM modes. If we will talk about the combination of the AFM with optical techniques, the idea here is not just to combine the two different instruments in one instrument, and the idea here is to increase the spatial resolution of quite well-known optical methods by use of the sharp AFM probe. And it is quite well known that there are three general approaches to it. First approach is to use tip-enhanced near-field optical microscopy, where there is a local enhancement of the scattered field by the probe. Another one is to use the specially created probes with the mechanically minimized aperture, and this approach is also useful, and it can give the spatial resolution down to 100 nanometers, some kind of this order. And the third approach, I will be focused on this approach in the last part of the presentation, is the scattering snow microscopy, where there is no local any amplification of the signal, but just there is an illumination of the area where the cantilever, where the tip of the atomic force microscope interacts with the sample, and then the backscattered light is analyzed somehow in its optical way. But before we will talk about, I would like first of all to mention that since the invention of atomic force microscopy, there are a lot of commercially available instruments have been developed, and one of commercial companies that produce this kind of instrumentation is our company, NTMDT Spectral Instruments, and we have the whole range of AFMs, starting from the quite regular desktop or even educational level AFMs, and up to professional fully automated microscopes for large samples investigations, and the systems that combines either Raman spectroscopy or infrared and terahertz spectroscopy and microscopy with the AFM. So the first part I would like to start with is actually refers to the very basics, to quite basic stuff of atomic force microscopy. That is, as we will see, is quite important for getting the proper images in all AFM modes or AFM-based methods. So, despite the atomic force microscopy is very well known and quite spread its method, still the AFM is a relatively slow instrument, and actually the instrument that is quite difficult to operate. The whole set of AFM modes can be split into three groups. The contact mode, where the cantilever is in constant contact with the sample. The so-called taping mode, or resonant oscillatory AFM, or semi-contact mode in Russian language, where the cantilever is oscillating near its resonant frequency, that is on the order of some kind like 100 kilohertz. And another group of modes is non-resonant oscillatory AFM, where either the chip of the probe or the sample oscillates on the frequency that is much lower than the resonance, about the frequency of the order of 1 kilohertz. And despite there are a lot of those kind of techniques, still, based on our analysis of the publications, more than 90% of the publications of the images that are published in peer-reviewed journals are made using the taping mode or taping mode-based techniques. Another important point here is that, in our understanding, about 20% of the images that are published in the peer-reviewed journals, taping mode images, contains the typical artifacts of the taping mode that refers to different kind of effects that I will talk about. And surprisingly, the percentage of the artifacted images almost does not correlate with the impact factor of the journal. So the idea of the taping mode, just a reminder, is that the cantilever oscillates on its resonant frequency, near its resonant frequency, then it touches the sample, amplitude of the cantilever oscillations is decreasing, and then during the scanning, the feedback system keeps this amplitude equal to some preset value, amplitude of set point, by moving the cantilever up and down, and then this position of the cantilever is then recognized as the topography of the sample. So during the measurements, we actually have several parameters that influence the quality of the result and influence the regime of the interaction of the probe of the sample. That is then, in consequence, influence the actually results if you apply if you make some near field experiments, or if you make some experiments in more complex AFM modes. So we have the amplitude of cantilever oscillation that can be larger or smaller, the set point value of this amplitude, the feedback gain, and the scan rate. And all these 4 parameters has a drastic influence to the quality and to the quality of the image. And any customer and any operator of atomic force microscope actually place all these parameters trying to get optical image as a and it is quite difficult. So the question is it possible to make it automatically? To make some technique that would allow to automatically adjust these parameters. And yes, it is possible, as we will see. But to understand it, how to do it, we have to briefly cover some very general stuff that occurs during the atomic force microscope interaction, to cover the parachuting effect, mode switching, and actually some general questions about the feedback gain operation. Okay, so suppose that we have the cantilever. This is quite simple, even the school level problem, but suppose we have the cantilever and we are scanning in the taping mode the step H. So we use the integral feedback for this, and well, of course one can use PID, but for the general consideration it's not so important. The feedback system works according to this equation. The output signal of the feedback system is proportional to the zero signal, that is and the coefficient here of the proportionality is the feedback gain. That is equal to the difference between the current amplitude of the cantilever oscillation and set point amplitude. The dependence of the cantilever amplitude on the distance is something like this. When we're far away from the surface, it is constant. When we are close to the surface, it is 0, and there is a linear part of this dependence. So we work somewhere here. So once we go to the step, the amplitude of the cantilever oscillation is quite fast. Within the time scale of the time constant of the cantilever itself drops to 0. As a result, we have the constant signal on the input of the feedback system, and we have the linear part, linear dependence on the measured topography. When we jump down from the step, we again have the linear dependence on the topography. And this kind of artifact, so-called parachuting artifact, is the most prevalent one in any AFM images published in any type of journals, including the highly reputable one. So first of all, it limits the area of the scanning parameters that can be used to get the proper image. And second, well, actually using some simple arithmetics, one can, using the forward and backward traces of the microscope, can compensate it. This is actually also useful for the phase images, for the phase contrast in atomic force microscopy. Maybe it's not the best quality of view here, but this is the phase signals on some polymer structure that are gotten on the forward and backward lines, and then after some simple arithmetics, it is these parts of the picture are much more contrast, and there are no topography artifacts here. So this is the first simple point, but despite it is quite simple, there are a lot of, once again, there are a lot of artifacted images published with artifact of this kind. The second point here is then, when we operate in taping mode, the interaction potential between the cantilever and the sample can be approximated in different ways, but independently on what kind of formula is used, some kind of these curves, blue curve will be plotted. So in this system, actually, there is possible when the cantilever jumps from the attraction regime to the repulsive regime, and this is the dependence of the cantilever amplitude on the distance between the cantilever and the sample at the different free amplitude. The smaller the amplitude, the closer to the surface the jump from the attraction to repulsion will occur. And the point here is that it is necessary to control and to understand what kind of regime of interaction do we have, and to adjust the system in the way so that the self-switching from the attraction to repulsion or back is not possible, because otherwise we will have artifacts not just on the topography, but in any other contours that are measured together with the topography. And the phase of the cantilever oscillations is a good science, and the system itself, it might be problematic for the operator to control it, but for the system itself, it's not a problem to control the phase of cantilever oscillations to understand if it is in attraction or repulsion regime. The third point here is actually the error of the measurements of the topography in taping mode is proportional to the scan velocity, some time constant, and derivative of the topography. This is a very simple relation, but it gives a quite simple idea. If we have a good scanner that allows us to scan with the, not with the constant scan speed, and if we want to keep the error signal within some limits, we can adjust. If we have the rough topography, so this derivative is higher, we can decrease the speed. Or if we have the quite flat sample, quite flat topography, we can decrease the speed of scanning. Indeed, it helps to save the probe and to get more robust images. So based on all this stuff, we made a system that we call the scantronic that allows to automatically optimize the scanning parameters, the amplitude of cantilever oscillation, set point values, scan speed, and feedback gain to get the images, taping mode images on different kinds of samples. This is an example of fluoralkanes adjusted manually. This is a fluoralkanes F14H20 on silicon surface. And once we try to scan them, this is quite a soft sample. If we try to scan with a gentle interaction, we get the parachuting effect images. It was just several seconds before. If we want to push it harder, we just damage the sample. But if we take into account all these quite basic things I was talking about, the system can be self-adjusted. And it makes it possible to get the high quality images even on those kind of quite tricky samples. And this is an example. So the scanning parameters and the whole state of the system of the microscope is adjusted automatically here. This is the topography and the phase contrast. And it is even clearer seen that it was damaged during the attempt to manually adjust the parameters. So this is the same example. In other examples of some kind of polymers like high-density polyethylene or polystyrene with polymethyl acrylate. There is almost no scientific meaning in these images, but the key point here is that the parameters are adjusted automatically. It works on the different kind of samples and different resolutions. This is the example of DNA origami self-assembly. The scan size here is 300 by 300 nanometers. And the system uses several lines, and by pressing one button, it automatically adjusts all these scanning parameters for this kind of tricky samples to get the image. And then it starts to scan, and we see this kind of triangles that is a self-assembled origami structures. Another example is polyvinyl denfluoride with polystyrene topography and phase imaging. The same sample is a closer look. Just one more note about it. If we start with the parameters, with the initial parameters that are more preferably that fits more, let's say, the atomically flat substrate, and we will start to scan some rough topography. This slide always takes a lot of likes during some online presentations. So when we start to scan some rough topographies, the cantilever might be damaged. So the initial parameters, the selection of initial parameters is important, and the machine learning algorithms are useful here, like the engineer who knows, dependently on if he has the rough topography sample or the flat sample, he knows it. And so the machine learning here solves this problem. And the second point, that what I was saying about the correlation between the scan speed and the topography roughness, if we able to change the velocity, the scan velocity during the scanning. So if we have the higher derivative of the topography, we can decrease the speed. And if we have a more flat part of the topography, we can increase the speed again. And this is the end membrane where the scanning parameters are automatically adjusted, and this scan of speed is very independent on if topography is rough or not. And then this function of the scan of the speed self-adjustment is turned on, and we can see those kind of artifacts that refers to actually the parachuting effect. This scratches. This is once again the most common artifact in AFM images. And when we turn on this function again, we again have the quite good image, but the probe is slightly damaged. Another example is the aluminum oxide that is actually the grater for tip. This is automatically made image, and this is the image that is made during the manual adjustment of parameters. At the end of the scan, the parameters are adjusted and they are quite correct, but during this adjustment process, the tip is damaged already, and one have to exchange the tip. So this was a simple part, but this is a quite new one, and we think that it is important. It is interesting and important for any applications of AFM, because once the basis, the taping mode parameters are not adjusted properly, and then we cannot move forward with more complex techniques like Kelvin mode or like optical technique. And we now switch to a brief part about the scanning near field optical microscopy. I will be focused on this type of the combination of optics and AFM. This is the Integra Nano IR system, the system that is developed for to realize the scattering snow microscopy. The idea here is quite simple. We have the AFM cantilever that is oscillating on its resonant frequency, and we have some external light of some spectral, within some spectral range. So the scattered light then is analyzed with the microson interferometer. And the dependence of the scattered field on the distance between the probe and the sample is quite nonlinear, is strongly nonlinear. So so on the doubled or tripled frequency of the cantilever oscillation, there is a response. There is an optical response that refers to the complex dielectric permittivity of the sample. So after the amplification with optical interferometer, then this signal is analyzed, and we can measure the optical amplitude and optical topography and optical phase of the scattered light. And this is an example of the phase-changing material, metamaterial vanadium dioxide, that is quite well known to have metal to insulator to metal transition within quite narrow temperature range from 27 to 67 degrees. This is and it is visible in these infrared images that it becomes conductive with this golden state. A little bit more experiments with the same materials on the both temperature dependence and strength dependence of this transition in vanadium oxide. So the check pattern substrate is used here, and depending on the stretch, so we have, when we cover the titanium oxide with the vanadium oxide, we have the area where it is quite flat, almost not stretched, where it is highly stretched, and where it is middle stretched. And the temperature dependence of the transition character is different for this area. Another example is the samarium sulfide, that is the heavy ferment materials that is also well known to have the transition from the black semiconductor to the golden matter through some intermediate phase when it is the relatively high pressure applied. And the good way to apply this pressure is the FM cantilevers to apply pressure, or is able to apply pressure of the orders of 10 to 20 kilobars. And these are examples of how this transition occurs. Another example is a MOT insulator to metal transition in MOT insulators induced by the apply of the external fields. All these examples and experiments are done by our customer on this system, and so one can see that there are some strike-like pattern occurs when applying the external fields, and sampled transfers from the insulator to metal state. It can be used for the dopant profiling in semiconductors. Two examples are here. This is P-type and N-type areas in some test structure and some metal oxide semiconductor structures. And it can be used even in terahertz ranges, the same ideology, and an example of the graphene studies in terahertz ranges are given in this slide. And the last example, that this system can be quite simplified to the visible to the scattering norm in the visible spectral range once it is robust and stable enough to operate with these wavelengths, and some patterns of plasma polaritons can be also measured in both in terms of optical amplitude and optical phase. So in the end of my presentation, I would like to thank my colleagues for collaboration, and thank you, and your questions very welcome.
Thank you for interesting talk. Thank you. Questions, please. Okay, I have a question. What's the spatial resolution in target frequency range?
Thank you for this question. The spatial resolution here is, let's say, about, in this particular, I would say that this is about 50 nanometers, 50, maybe 100 nanometers, something like this.
And how can it enhancement this resolution?
Well, actually, to use the sharper probes, because the resolution depends on the probe sharpness, if the probe is sharper. But once you have the sharper probe, you have to spend more time just collecting the enough signal in any point of scan. So in principle, the infinitely sharp probe can be used if you have the infinite time to and zero drifts of the system to collect all those images. For example, this scan was this is a quite time-consuming experiment, and this scan are done with the scan rate of the order of 0.03 hertz. So for each line, it is like 1 divided to 0.03 seconds. So this scan requires several hours to be collected.
Okay. Any questions? Okay.
Well, I have two questions. So one, if you could go back to the phase change materials.
To which one?
Example, like of I understand it was like just demonstration of phase change material, the crystalline amorphous phase. Am I right? Sorry, just yes, this one.
Mm-hmm.
Is it is there any possibility to do the in situ study? Like, do you observe any, can you obtain any interesting information from the in situ heating and changing the state of the material?
Thank you for this. This is a good question, and this is actually, I would say this is almost in situ studies. So you have this kind of structures, and you change the temperature with a relatively small step, and you can see that from scan to scan, the part of the insulating and already transited to conductive phases are different. So this is what actually can be done. But the time, this is of course, but the time required to collect the signal is quite. This is within the times that are typical for AFM, or even larger for AFM, because you have to wait until you get enough optical signal to.
That's interesting, because, we can maybe discuss it later. And another question is about the liquids, fluids. Like, do you have any, haven't demonstrated any, capabilities of this technology for the fluid studies, or the surface of the fluids, or, do you have...
surface of the fluids or surface in fluids?
Both.
Both, thank you. Well, first of all, the AFM fluids in different regimes are widely used, and of course we can do it. I just didn't mention it in this presentation. The second one, the optical combination of optics and IFM is also possible. For example, the tip-enhanced phenomena, so liquid, are possible to obtain. I didn't show these examples, but they do exist, and we have this.
Thank you very much. We'll discuss this later. Thank you.
Any questions? So thank you again. The next talk will be given by Muhammed Abdullah Anatmaz from Ankara Ildirim Beyazıt University, Turkey. The title of his talk is Design and Characterization of Integrated Spoof Surface Plasmon Polaritons, please.
Good afternoon. I am Muhammed Abdullah Unutmaz from Ankara Yıldırım Beyazıt University, and thanks for inviting me to give this talk in this beautiful city. In the beginning of my career, I was dealing with radar and telecommunication systems, and I wanted to continue with integrated systems. And currently, I am working on integrated micromachine waveguides for terahertz. I am going to talk about terahertz technologies and applications, possible potential markets and current terahertz market, potential of smooth surface plasmon polaritons for terahertz coupling in corrugation waveguides, and modeling of smooth surface plasmon polaritons for both side corrugated planar structure, and its verification with currently available measurement setups in the market. And finally, I am going to talk about applications of this structure as fixed physical length delay lines and MEMS configurable integrated smooth surface plasmon polaritons. The terahertz spectrum range from 0.1 to 10 terahertz region of the electromagnetic spectrum, and it is invasive. That's why it has great potential for remote sensing and spectroscopy. Remote sensing and spectroscopy are two of the most common applications of terahertz technologies, and the total market size of the medical imaging is expected to excess $45 billion by 2023, and the current technology is based on ultrasound imaging, MRI, which is microwave region, and X-ray based system, namely X-ray equipments, CT scanners, nuclear imaging equipment. However, terahertz gap has not taken its place in medical imaging market, according to the current research market analysis. And when we consider the problem is in terms of the wavelength, and by considering the radar cross section, X-ray based systems are perfect solutions for high resolution imaging, but however they are risky for health. On the other hand, ultrasound imaging and MRI imaging are much safer solutions. However, they provide lower resolution. And terahertz imaging systems are in between these wavelengths, and they provide either high resolution and safe imaging compared with microwave and X-ray. And the 5G market, which is coming, is expected to access 5G services market is expected to access $100 billion by 2025, and the global 5G market is expected to access $250 billion. And 5G bandwidth is compared with 1 gigabit per second. On the other hand, in terrestrial systems, the bandwidth will be in tens of gigahertz. CPU market is also another potential area for terrestrial systems, and it is expected to. It is already there around $75 billion, maybe larger. And despite the fact that the transistors have been shrinking in size, and they are becoming faster, the bus speeds are the two main legs. Bus speeds are lacking the. Sorry, bus speeds are lacking the CPU performances. And when we are talking about the entire terrestrial market size, global market size, we are talking about $0.4 billion. When comparing the other markets, it is really a huge gap. And subsurface plasmon polaritones have great potential for integrated terrestrial systems. The subsurface plasmon polariton term was first introduced by Pendry and others at 2004, and the current motivation is to provide solutions by using massive reconfigurable devices. Why it has great potential? Because it is a very wide range of effective dielectric constant within a single period and same physical length period. 8 to 40. And with corrugations, they provide improved confinement. And thanks to the wide range of effective dielectric constant and large amount of effective dielectric constant, miniaturization of the integrated terrestrial components are possible. That's why signal integrity issues could be minimized, and by using subsurface plasmon polaritons, it is possible to once they are integrated with high-speed CPUs, CPU market, as a domino effect, telecommunications and medical imaging market could be expedited. The main goal of my study is to design fixed physical length reconfigurable terrestrial delay lines with subsurface plasmon polaritons. However, in the beginning, there was no reliable formula for effective dielectric constant. That's why I started with investigation of how to solve this problem. The general design approach, all of which are for microwave and PCB technology, were investigation of dispersion diagram and extraction of the effective dielectric constant. In the beginning, I had to fundamental questions because I was totally unfamiliar with terrestrial applications. If metal properties were like perfect electric conductor, or they are similar to optical band behavior. and measurement was the most critical problem for me. Because for verification, I needed to compare either simulations and the measurements. For visualization of the coupling, I started with domino plasmon structures, and I repeated a problem which is available in the literature. As you can see, the field is very well confined between the gratings. For my problem, effective dielectric constant modeling problem, I had 6 different variables, namely corrugation depth, periodicity, aperture width, and substrate properties, relative permittivity, and substrate thickness, and metal thickness. However, the coupling of the wave to this structure was in a measurement setup was the most critical problem. To solve this problem, I use conventional waveguide for excitation, namely SPw waveguides as the excitation section. Then transition sections for mode conversion, and I put the SSBP the delay section between the transition sections, and for examining the effective dielectric constant data, I compared the electrical lengths of these devices with a reference waveguide without any supersurface plasmon polarity section. To solve my problem, I employed a solution of a mathematical problem of single side corrugated structure, because the propagated mode is even mode, and to convert the physical dimensions to the mathematical solution domain, I defined the mapping wavelength, and for verification of my solution, as I mentioned, I designed a group of waveguides and fabricated and measured these devices. I needed to apply an empirical solution because why the entire structure for the metallic corrugated single side metallic corrugated structure was everything was metal. Here I have the electric material which confines the confines the wave also inside itself. And the complex analysis solution I usualize is converse the physical dimensions, the period, corrugation depth, and the metal width for my problem into a linearly distributed solution domain, and conversion for back conversion. Another mapping function is utilized in the solution. However, this is only for single side corrugated structure. While in my problem I had substrate thickness, relative permittivity, and metal thickness. And for verification, as I mentioned, I designed a reference waveguides and a group of spoof surface plasmon polarity delay lines. And since it is cheaper and easier to implement, I started with microwave regime, and this is the formulation for the microwave band. I achieved an error rate around 6% for these devices, and as you can see, the S-parameter measurements meet each other very well. Then I applied the same approach for terahertz band. I investigated very large group of parameters and examined the solution at three different frequencies: 0.25, 275, and 0.33 terahertz as a function of where the mapping wavelength is at the is the intrinsic wavelength at these frequencies. And I fabricated these devices with a single mass process. I use high resistivity silicon wafers, spin coating process, sputtering, and lift-off processes for a critical feature size of 2 micron. And for verification, I use the contactless probing solution by teleprobes increment. It is based on the calibration method is based on Kuiko's offset shorts, whose error minimization the diagram is here, and we compare the group of known devices to verify the calibration, and the first time comparison of the simulation and measurements results of my studies here. Before my study, only two measurements for these devices were available in the literature. I found these comparisons are for 21 different devices. And I have achieved an average error rate better than 3% for these devices. I continued with the design of fixed physical length smooth surface plasmon polarity delay lines. In the delay lines, I only determined the corrugation depth for the same length, same physical length delay lines, and calculated the effective dielectric constants for the different corrugation depths only. And here is a group of microwave delay lines. I also use these devices for extraction of the investigation of the losses. Here are the error rates, and average error rate is around 0.43 dB. And I applied the same approach for terahertz band, and for having 90 degree, 180 degree, and 275 degree phase shifters. Their simulation and measurement comparisons are here. And I continued with the design of MEMS configurable terahertz full surface plasmon polarity circuits for a 90 degree phase shift. I applied a 6-mask mass fabrication process. I use high resistivity silicon substrate, silicon chromium sputtering, chromium gold evaporation, sacrificial layer, and dimple patterning, gold sputtering, and gold electroplating. And here are the first time fabrication of the MEMS reconfigurable smooth surface plasmon polarity for terahertz. And here are the SEM images of the devices. This process is not perfect. However, I know only one thing I need to optimize, and here are several MEMS devices which are smaller. All the dimensions of these devices are smaller than 10 micrometers. And actually, for me, this is the most important question for terahertz, because when we are trying to integrate these devices into a system, we want the system to work stable without changing in any parameters in time. And actually, I am curious about how long these devices and what power levels these devices work for. In optical band, the device parameters may be very sensitive to the temperature and power level, and I am curious about what will happen in terahertz regime. Here I want to thank Kubilay Sertab from Ohio State University and Teleprops Increment, because without their support, we couldn't measure any one of these devices. I also want to acknowledge Mr. Orhan Akar and Mitümen's personnel for their education and support in mass fabrication processes. I talk about TRI technologies and applications, potential markets and current TRI's market coupling mechanism, and potential of smooth surface plasma polaritons and their applications. Thank you very much for your attention.
Thank you. Questions, please. I have a question. What's the propagation length of your surface plasma for tropospheric consideration?
Propagation length, I think you are asking losses.
Yeah.
For these devices, we also investigated the losses at 0.3 terais. The length of the SSPP delay section is around 1 millimeter, and the average loss is approximately 3 dB for these devices. Maybe it can seem very lossy. However, the beautiful side of this study for me is modeling and mass fabrication.
Okay. Any questions? So thank you again. The next talk will be given by Professor Vladimir Osipov from YOF Institute, Russia. The title of his talk is Photoluminescence from NV Centers in 5 nanometer detonation nanodiamonds, identification and large sensitivity to magnetic field. Please.
Hello everyone, I am Vladimir Osipov, senior scientist from YOF Institute. The theme of my presentation is photoluminescence from nitrogen vacuum centers in 5 nanometers detonation nanodiamonds. Sorry. Okay. This is my collaborators. So the first team is the team from Paris-Saclay University, the team of Professor François Drissot, then the team of Professor Kazuyuki Takai from Hasei University in Tokyo, Japan, then my collaborator Dr. Fedor Shakhov from YOF Institute, and also I am collaborating with a group of Professor Anna Baldasheva. So the main results obtained by us were obtained in Japan, in Hasei University, and in the group of Professor François Drissot. Okay. So my speech is about diamonds and nitrogen vacuum centers in diamonds. So here you can see the picture of diamond lattice, and this is the nitrogen vacancy center. So this is the substitutional nitrogen atom, and this is the vacancy. So a lot of people suppose now that nitrogen vacancy centers is the gift of nature to the mankind. Why? Because by means of NV centers, we can obtain a lot of very promising applications. For example, they can be used in telecommunication, in quantum cryptography. They can also be used as a source of single photons. Also, they can be used in bioimaging and also for drug delivery and for anti-cancer therapy. So why diamonds and nanodiamonds are very promising for bioimaging? Probably you know that all living tissues have a window for has a window in the infrared region, and red radiation can easily penetrate to the biological tissues. Okay. So this is just example how can we use fluorescent diamonds for bioimaging. So here you can see just the simple image of some sarcoma cell. The diameter is about 10 microns here, and this is just image obtained by ordinary microscope by means of phase contrast microscopy. And here you can see the fluorescent image of the same sarcoma cell surrounded by nanodiamonds. This image was obtained in the red channel, and this image was obtained in green channel. So, here nanodiamonds play two roles. One role is for decoration the periphery of cells, and another role is for delivery of some drug molecules inside the cell. So this image was obtained in the group of Professor François Trousseau, and I use this image just for example how we can use diamonds, fluorescent diamonds, for bioimaging. Okay, but for this experiments we used very rough diamonds. So the size of these diamonds was about 50 nanometers. So 50 nanometers is very large diamonds. They cannot penetrate through the cell membranes inside the interior of cells. And for this purpose, we need to use much smaller nanodiamonds with a size between 5 and 10 nanometers. For this purpose, for obtaining much smaller nanodiamonds, we used another commercial product. So this scheme illustrates how detonation nanodiamonds can be synthesized by means of detonation synthesis. This is a detonation chamber, and various explosion of some explosive substances inside. Here you can see the schemes for molecules of TNT and hexagon, and the explosive substance is the mixture 50-50% of TNT and hexagon. And you can see that each explosion molecule consists of carbon atoms, nitrogen atoms, and oxygen. So carbon atoms of explosive molecules contribute to the assembling of diamond crystals. And here you can see also nitrogen atoms, and nitrogen atoms appear automatically inside growing diamond nanocrystallites as nitrogen substitutional impurities, and also they contribute to the appearance of NV centers inside. So the mean size of detonation nanodiamonds is about 5 nanometers. So this is the new product, and it is available on the global market. There are a lot of plants in the world for synthesis with diamonds. One plant is in our city in St. Petersburg, and there are a few plants in China, and I know one plant in Japan. Okay, next slide. So for characterization nanodiamonds, we used electron spin resonance. So this is the photo of electron spin resonance spectrometer. And this is the microwave resonate cavity, and this is the electromagnet. Okay. On this slide, you can see the electron spin resonance spectrum of detonation nanodiamonds. Here you can see the single line. So this line is related with a large contribution of paramagnetic centers, and paramagnetic centers in nanodiamond are related with the next defects. First of all, we can consider dangling bond spins with spin half, then so-called P1 centers with also spin half. P1 centers means just substitutional isolated nitrogen, and then we can expect vacancy-related centers here, like vacancy centers with hydrogen on site, and simply -1 charged vacancies also of spin half. And here you can see just a simple model of a detonation nanodiamond particle with about 15 paramagnetic centers inside. So the concentration of spins in one particle is very high. So it's about 17 spins per particle, or in other terms, about 1,200 or 1,600 ppm. ppm, maybe you know, means parts per million. And this is the image of detonation nanodiamond powder. This is the powder of gray color in a quartz ESA tube. Usually quartz ESA tube are used for inserting the sample inside the ESA spectrometer. Okay, next slide. This is the image of microwave cavity. You can see here the end of quartz tube with detonation nanodiamond powder of gray color. And usually we use such amount of powder for characterization. Usually we use about 25 or 30 milligrams of powder for characterization. So our task was to calculate exactly the concentration of nitrogen vacancy centers inside detonation nanodiamonds. So for this purpose, we use the reference sample. As a reference sample, we used the microcrystalline diamond obtained by means of high pressure, high temperature technique, and thereafter irradiated by high energy electrons. This is also the commercial product. And this synthetic diamond with nitrogen vacancy centers are very good sources of red radiation. So we compared commercial synthetic diamond with our detonation nanodiamond. So you can see that there are many lines on the spectrum. So line 1 is related with nitrogen vacancy centers in detonation nanodiamonds. This line is here for synthetic diamond, and line 1 with G factor 4.27 is related with so-called forbidden microwave transition in triplet centers. And this line and this line are related with allowed microwave transition in synthetic nanodiamonds. So the main feature of detonation nanodiamonds is the presence of only forbidden microwave transitions in absorption, and there are no any lines related with allowed microwave transition in detonation nanodiamonds. So on this figure you can see just the scheme for explanation the meaning of forbidden transition and the meaning of allowed transition. This three lines are related with triplet center, triplet nitrogen vacancy center with spin 1. And after applying magnetic field, there is the Zeeman splitting between energy levels with magnetic number 1 and magnetic number -1. And these transitions are related with absorption of microwave radiation. So forbidden transition means the change of magnetic number just on 2. And allowed microwave transitions means the change of magnetic quantum number on 1, from 0 state to +1 state. Okay, next slide. And we obtained some mathematics and some integration procedures for analyzing the integrated intensity of line related with nitrogen vacancies. So this is the graph for, this is the spectrum of first derivative signal, and this is the spectrum of the same, the graph of the same spectrum just after integration. So in order to evaluate the integrated intensity of this line correctly, it is necessary to subtract some background. So after subtraction some background, we obtained the same pretty signal, which consists of two lines. This line is related with nitrogen vacancy centers, and this line is related with so-called devacancies. Devacancies are also spin 1 triplet centers in detonation nanodiamonds, and this is the spectrum after integration for synthetic high pressure, high temperature diamond provided by our supplier from United States. So our supplier informed us that according to his opinion, the concentration of NV centers in his diamond was about 4.8 ppm, and in our case we found that double integrated intensity of line related with NV center was 4.5 times smaller than for reference sample. Thus we concluded that concentration of NV centers in our nanodiamonds is about 1.1 ppm. So this is, for today, this is the largest known concentration of NV centers in products with size less than 8-10 nanometers. I want to mark that that concentration of all types of paramagnetic species in nanodiamonds is very large. It's about 1030 ppm. So concentration of color centers is about 3 orders of magnitude smaller than concentration of all paramagnetic centers in diamond. And our estimation was also confirmed by some simple theory. When I calculated the probability to find one nitrogen vacancy center in nanodiamond, I obtained the same value. It means that only one particle from 100 particle has color center, but this is enough for the tasks for bioimaging. Okay, this graph illustrates just X-ray photoelectron spectra for nanodiamond. And here you can see the N1S line. It's related with interior and exterior nitrogen. So I want to mark that full concentration of nitrogen in detonation diamonds is very high, is about 1.6 atomic percent. So main part of atomic nitrogen in nanodiamonds is contained in the form of aggregates, in the form of nitrogen-nitrogen pairs. And nitrogen-nitrogen pairs has spin 1 and do not contribute to the SR signal. Here you can see just Raman scattering data for detonation nanodiamond. This G line is related. D line is related with the signal. Raman scattering signal from diamond lattice. This line is enough narrow. This line located at 1,100 reciprocal centimeters is related with so-called trans-polyethylene chains on the nanodiamond surface. This line is related with sp2 graphitic phase. And this line are related with carbonyl and carboxyl groups on the nanodiamond surface. This spectrum was obtained under excitation radiation about 325 nanometers. Okay. We also studied the luminescence spectra and their dependence upon the X-ray crystal size. So here you can see just typical luminescence spectrum of detonation nanodiamond. It has maximum around 680 nanometers, and this spectrum is related with own optical emission of NV center. So you can see that the band of NV emission is enough wide. It spreads from 600 up to 800 nanometers. And we analyzed different detonation nanodiamonds, and we found that the more nitrogen content in nanodiamond, the less nitrogen vacancy PL intensity in the spectrum maximum. Okay. Here you can see just confocal fluorescence microscopy images obtained after seizing nanodiamond particle on the glass cover slip. So here you can see a lot of images of nanodiamond aggregates. We investigated photoluminescence spectra of isolated nanodiamond aggregates and found they are practically the same. And the size of aggregates is about 1 or 200 nanometers here. And here you can see on the image you can see also a lot of small spots. And these spots are related with smallest aggregates of nanodiamond particles, or maybe with isolated nanodiamond particles. So I especially plotted here a lot of straight lines, and you can see that we can see that some particles, some isolated nanodiamond particles, lays on these lines, and these lines are related with multiple scratch on the cover slip. So here you can see 1, 2, 3, 4, 5 particles on one scratch. Okay, and also we in group of Professor Francois Trousseau, we did one very famous experiment. We checked the influence of permanent magnetic field on the luminescence of detonation nanodiamond aggregates, and we found that after applying enough enough magnetic field, not strong, with value about 100 millitesla, there is a strong decrease in luminescence. And we obtained this data by approaching the permanent magnet close to the disposition of nanodiamond particles. See, you can see the telegraph-like behavior independence of approaching or removal of the permanent magnet. And this phenomena is related with spin level anti-crossing. So it happens when this Zeeman splitted line with quantum magnetic number -1 intersects with this level. And when this event is happened, then the luminescence drops. So we observed this phenomenon first time for 5 nanometers detonation nanodiamonds. But before us, many people observed this phenomenon for bulk microdiamonds. But in our case, the drop in PL intensity is very large. It's about 75% of the maximal intensity of luminescence. Is much more than value reported before in the literature. So my conclusions. So first time we evaluated the concentration of NV color centers in detonation nanodiamonds, and this value equals 1.1 ppm. And first time we observed the influence of external magnetic field on the PL intensity of detonation nanodiamonds. So at the end, I want to say our gratitude to several grants. So this work was supported by 2 Japanese grants and by 2 grants from European Union. Thank you for your attention.
Thank you. Questions, please. I have a question. How does the temperature changing influence on the dependence of photoluminescence on a magnetic field?
Photoluminescence?
How the temperature impact on the dependence photoluminescence on magnetic field?
On magnetic field?
Yeah, yes.
Okay. So first of all, we specially did not study the dependence of temperature on the dependence of photoluminescence upon magnetic field, because experiment is very complicated. It's very easy to study the dependence of photoluminescence upon temperature itself, but very difficult to study the dependence upon the magnetic field. So my answer is no, but if you are interested in dependence upon temperature, I can say you that the shape of PL spectra, the shape of PL spectrum depends very strongly upon temperature, because this I can show, sorry. Okay, this is the typical shape of PL spectra for diamonds having nitrogen vacancy centers. And this band is related with so-called side phonon band. So this is just phonon band, and that is why this band is very wide. And after cooling with this sample down to nitrogen temperature or down to helium temperature, the side phonon band disappears. where width equals practically 0. And for example, at helium temperature, we have only one zero phonon line, very narrow, with the width about maybe between 2 or 5 nanometers. That's all.
Okay. Any questions? Okay, please.
Yeah.
Do you want to have low concentration of NV centers or high concentration, or you just want to characterize?
Okay. It's a very important question, because many people in literature discuss the importance of high or low concentration of nitrogen vacancy centers. So the task which I solved in this research was just first evaluation concentration of NV centers in nanodiamond. But in case of a commercial product, sometimes having large concentration of NV centers is not good, because having larger concentration of NV centers, the absolute value of luminosity of irradiated emission drops, because many centers work as quenches of luminescence. So the answer for production, for producing the maximal output of optical radiation, we need to find optimal concentration of color centers. So just optimal concentration of color centers works okay.
Okay, any questions? The last question. What's the quality factor of your microwave cavity? What's the minimal concentration of these sensors you may register?
Yeah, it's also very interesting question. Okay, for example, just this is our ESR spectrometer. We used Japanese ESR spectrometer, and the Q factor of this microwave cavity is about 7 or 8 thousandths. But so the minimal concentration maybe is around so it's difficult to answer, but I understand your question. But if we will use more material, yes, we can increase the number of paramagnetic centers. But really, answer depends upon the amount of material in cavity. But at the moment, I don't know the absolute value of spin radicals.
Okay. Thank you again.
Thank you.
Session will be given by Georgy Yermolayev from Moscow Institute of Physics and Technology, Russia. The title of his talk is Optical Constant of Bulk and Two-Dimensional Molybdenum Disulfide. Please.
Okay. Good afternoon, everyone. My name is Georgy, and I present Moscow Institute of Physics and Technology and Skolkovo Institute of Science and Technology. My topic is optical constants of bulk and two-dimensional molybdenum disulfide. As you know, molybdenum disulfide is a member of transition metal dichalcogenides, which are very important nowadays because they have a unique optical properties. And you will see why. I'm going to tell you about basic of transition metal dehalogenide physics. Then I will tell you about ellipsometry. It's a technique which allows to obtain optical properties directly. Then I will show you the results of this technique. And also, I will explain the physical background of these optical constants. And you will see how dark excitons transform into bright excitons. So let us begin. Transition metal dehalogenide. I will focus mainly on two-dimensional case because from my point of view it's much more interesting. Okay, monolayer transition metal dehalogenide consists of one layer of transition metal. It could be molybdenum, tungsten, and so on. And this layer sandwiched between two layers of chalcogen, and it could be sulfur or selenium. And if you see on the top, on this structure, it looks like graphene. It's a honeycomb structure. And because of that, in effective Hamiltonian has a graphene-like part. However, unlike the graphene, the atoms are different. And that is why in effective Hamiltonian, we have a sigma Z part, which opens the gap in band structure. And it means that transition metal dehalogenide are semiconductors. What is more, because we have a monolayer, for electrons feels the quantum confinement in a perpendicular direction to monolayer. What is more, if we consider interaction between holes and electrons, then hole and electrons don't only interact with each other along the material, but also outside the material, where the screening is mainly reduced. And because of that, interaction between hole and electrons becomes very enhanced, and it leads to enhanced Coulomb interaction between hole and electrons. Because of that, under light illumination, this light induce excitons, even at room temperature, because this very high Coulomb interaction between electron and holes. This leads to a very high absorption for monolayer. It's about 20% for monolayer. And it's also, this material very promising for excitonic application. For example, as Pavlos Volgodakis said, it could be used for exciton polaritons. Okay, and these materials already found a lot of applications in light-emitting diodes, in solar cells, and ultra-sensitive photodetectors, and etc., etc. What is more, for all these applications and for optoelectronic applications, it is vitally important to know optical constant. And for this, ellipsometry is a good way to go. Ellipsometry is a spectroscopic technique which measures the change of light polarization. So we send linearly polarized light. After interaction, it becomes elliptically polarized, and ellipsometry measure the parameters of ellipse. And it's the major advantage of this technique is that it's very sensitive to thin films. Because we have a monolayer, it's extremely sensitive for monolayer, and it's very useful for investigation of two-dimensional materials. However, it has a major disadvantage that it's very hard to analyze, because we need to build a physical model in order to analyze spectra. It means that you provide a physical model for molybdenum disulfide, and based on this model, you compute psi and delta, and compare this with experimental one. If they coincide, then you choose the right model, and everything is okay. If they are not, you should find another model. However, in case of molybdenum disulfide or another transition metal dehydrogenase, the physical model where should we start is clear, that we should start from excitonic nature of this material. Excitonic nature is for these materials is well described by Tau-Lorentz oscillator, and on the slide you can see the formula for Tau-Lorentz oscillator for imaginary part of the electric function and the shape of the dielectric function. So we apply this approach and it works. It gives the following results. On the left slide you can see the real part of the electric function, and on the right part you can see the imaginary part of the electric function. So far we completed our goals and get optical constant, but let us investigate what we obtain, because in our approach we use one oscillator Tau-Lorentz for each exciton. It means that we artificially separate the contribution from different excitons, and we can investigate them individually. For example, on the bottom you can see the comparison of our results of this individual investigation with the previously reported work, and you can see that the orange line, which is our results, is very close to the previously reported works for typical A, B, and C excitons. What is more, in our obtained spectra we have 2 additional peaks which has not been published before in optical constants, and the question is what is the origin, physical origin for these peaks? For the blue one, the answer is quite simple. It's the excitonic series of A and B excitons. So it's just 2s, 3s, and so on excitons. However, for this peak, the answer is much more complicated. Because we find out that for some samples, we see these peaks in optical constant, but for another we didn't see them. And we start to investigate this question, and all our samples are chemical vapor deposition grown on silicon dioxide, and we noticed that for samples where TAS molecule was used during the synthesis, we observed this peak, while for samples where the TAS molecule was absent, the peak is absent as well, the blue line. And the recent theoretical results show, in fact, that the molecule on top of the metal dihydrogenase, in fact, could induce dark excitons. So before placing the molecule on the metal dihydrogenase, there are only 1 peak, but when we placed molecule on our metal dihydrogenase, we observe 2 peaks in spectra, and that is our results is coincide with this theoretical works. The theoretical works was for tungsten disulfide, that is why you can see the dark exciton left. But for molybdenum disulfide, it should be, in fact, right. Okay, that brings me to the end of my talk. Let me go over the key points again. We obtained optical constants, and we discussed the physical origin for these optical constants. And also we observed 2 new features. One feature is not new, but they wasn't published. It's excitonic series in optical constants. And another feature, which is was recent result, that we observed a transformation of dark exciton into bright exciton due to presence of molecule on the top of our samples. Thank you for your attention. If you have any question, I'll be happy to answer to them. Yes?
Am I correct that you did modeling only, you did not do experiment?
No, I did the experiment.
You did experiment?
I did experiment, yes, and I investigate all this. No, I did it not by myself. No, not experiment I do by myself, but most of them I do by myself. Because, as you see, ellipsometry technique, it measures the samples in like, it depends on the parameters, but it took, and depends on the ellipsometry, it took 4 minutes or maybe 1 hour, so it's very fast, but the major difficulty is to analyze spectra because it changes the polarization and nobody thinks in the polarization and it's difficult to analyze. And that is why it's, we should provide physical model and investigate physical origins. And that is advantage in one hand because we not only obtain optical constant, but we obtain physical origin of this constant. However, the major disadvantage that it's difficult to analyze. Yes. Yes. We know the properties of the, we know properties of silicon, we know the properties of silicon dioxide, then molybdenum disulfide is placed and we measure and we should provide only physical model for molybdenum disulfide, yes. So if we placed on the other substrate, we should also investigate the substrate as well. But in our case, we know everything about the substrate. Okay?
Where did you grow?
You mean molybdenum disulfide? Most of them we didn't grow by ourselves. We bought it from 2D semiconductors company, and some of them were grown in MIPT. Some of them was bought in another company. I don't remember the name. Some of them was ours, but most of them is not ours. Yes, you have a question? No.
Azimuth angle value, ellipticity angle value after interaction?
It becomes, how to say, I didn't mention it, but also we should, this type of materials interacts differently on right-hand side polarization and on left-hand polarization. And this left-hand side and right-hand side gives us different polarization, and it gives us ellipse. Yes. And you know that also it's difficult to answer because we measure the spectra for broad wavelengths, and for each wavelength it's a different special azimuthal angle and so on. Yes.
Thank you. Thank you again. Now it's
Okay, I can resonate. I actually would like to thank all the speakers for today and for the last 3 and 4 days of both conferences. This actually was the last session for this SPb-POEM conference. We continue with the networking over the coffee break, the last coffee after this session. And also, I would like to remind you, we have a boat trip tomorrow, so it's going to be an excellent environment for networking again and discuss all the presentations during this conference. Thank you very much for attending this conference. So let's move and have a coffee. Thank you very much, guys.